A wavelet is a wave-like oscillation with an amplitude that begins at 0, increases, and then decreases back to 0. It can typically be visualized as a brief oscillation, like one might see recorded by a seismograph or heart monitor. Generally, wavelets are purposefully crafted to have specific properties that make them useful for signal processing. Wavelets can be combined using a reverse, shift, multiply and integrate technique called convolution with portions of a known signal to extract information from the unknown signal. For example, a wavelet could be created to have a frequency of middle C and a short duration of roughly a 30-second note. If this wavelet was to be convolved with a signal created from the recording of a song, then the resulting signal would be useful for determining when the middle C note was being played in the song. Mathematically, the wavelet will correlate with the signal if the unknown signal contains information of similar frequency. This concept of correlation is at the core of many practical applications of wavelet theory. As a mathematical tool, wavelets can be used to extract information from many different kinds of data, including, but certainly not limited to, audio signals and images. Sets of wavelets are generally needed to analyze data fully. A set of complementary wavelets will decompose data without gaps or overlaps so that the decomposition process is mathematically reversible. Thus, sets of complementary wavelets are useful in wavelet-based compression, decompression algorithms where it is desirable to recover the original information with minimal loss. In formal terms, this representation is a wavelet series representation of a square integrable function with respect to either a complete, orthonormal set of basis functions, or an overcomplete set or frame of a vector space, for the Hilbert space of square integrable functions. Name. The word wavelet has been used for decades in digital signal processing and exploration geophysics. The equivalent French word onde-lettre meaning small wave was used by Morlet and Grossman in the early 1980s. Wavelet theory. Wavelet theory is applicable to several subjects. Almost all practically useful discrete wavelet transforms use discrete time filter banks. These filter banks are called the wavelet and scaling coefficients in wavelets nomenclature. These filter banks may contain either finite impulse response or infinite impulse response filters. The wavelets forming a continuous wavelet transform are subject to the uncertainty principle of Fourier analysis respective sampling theory. Given a signal with some event in it, one cannot assign simultaneously an exact time and frequency response scale to that event. The product of the uncertainties of time and frequency response scale has a lower bound. Thus, in the scaleogram of a continuous wavelet transform of this signal, such an event marks an entire region in the timescale plane, instead of just one point. Also, discrete wavelet bases may be considered in the context of other forms of the uncertainty principle. Wavelet transforms are broadly divided into three classes: continuous, discrete and multi-resolution based. Continuous wavelet transforms. In continuous wavelet transforms, a given signal of finite energy is projected on a continuous family of frequency bands. For instance, the signal may be represented on every frequency band of the form f to f for all positive frequencies f greater than 0. Then, the original signal can be reconstructed by a suitable integration over all the resulting frequency components. The frequency bands or subspaces are scaled versions of a subspace at scale 1. This subspace in turn is in most situations generated by the shifts of one generating function psi in L2, the mother wavelet. For the example of the scale 1 frequency band 1, 2, this function is with the sinc function, that Mayer's, and two other examples of mother wavelets are the subspace of scalar or frequency band 1, A, 2, A is generated by the functions where A is positive and defines the scale and B is any real number and defines the shift. The pair defines a point in the right H-plane R plus times R. The projection of the function x onto the subspace of scalar then has the form with wavelet coefficients. See a list of some continuous wavelets. For the analysis of the signal x, one can assemble the wavelet coefficients into a scaleogram of the signal. Discrete wavelet transforms. It is computationally impossible to analyze a signal using all wavelet coefficients. So one may wonder if it is sufficient to pick a discrete subset of the upper H-plane to be able to reconstruct a signal from the corresponding wavelet coefficients. One such system is the affine system for some real parameters a greater than 1, b greater than 0. The corresponding discrete subset of the H-plane consists of all the points with m, n in Z. The corresponding baby wavelets are now given as a sufficient condition for the reconstruction of any signal x of finite energy by the formula is that the functions form a orthonormal basis of L2. Multi-resolution-based discrete wavelet transforms. In any discretized wavelet transform, there are only a finite number of wavelet coefficients for each bounded rectangular region in the upper H-plane. Still, each coefficient requires the evaluation of an integral. In special situations, this numerical complexity can be avoided if the scaled and shifted wavelets form a multi-resolution analysis. This means that there has to exist an auxiliary function, the father wavelet phi in L2, and that a is an integer. A typical choices are equals 2 and be equals 1. The most famous pair of father and mother wavelets is the Doubek's 4-tap wavelet. Note that not every orthonormal discrete wavelet basis can be associated to a multi-resolution analysis. For example, the Gen wavelet admits no multi-resolution analysis. From the mother and father wavelets one constructs the subspaces. The mother wavelet keeps the time domain properties, while the father wavelet keeps the frequency domain properties. From these it is required that the sequence forms a multi-resolution analysis of L2 and that the subspaces are the orthogonal differences of the above sequence. That is, Wm is the orthogonal complement of Vm inside the subspace Vm-1. In analogy to the sampling theorem, one may conclude that the space Vm with sampling distance 2 meters more or less covers the frequency baseband from 0 to 2-m1. As orthogonal complement, Wm roughly covers the band 2-m-1, 2-m. From those inclusions in orthogonality relations, especially, follows the existence of sequences and that satisfy the identities so that the second identity of the first pair is a refinement equation. For the father wavelet phi, both pairs of identities form the basis for the algorithm of the fast wavelet transform. From the multi-resolution analysis derives the orthogonal decomposition of the space L2 as for any signal or function. This gives a representation in basis functions of the corresponding subspaces as where the coefficients are in mother wavelet. For practical applications, and for efficiency reasons, one prefers continuously differentiable functions with compact support as mother wavelet. However, to satisfy analytical requirements and in general for theoretical reasons, one chooses the wavelet functions from a subspace of the space. This is the space of measurable functions that are absolutely and square integrable, and being in this space ensures that one can formulate the conditions of zero mean and square norm. 1 is the condition for zero mean, and is the condition for square norm 1. For psi to be a wavelet for the continuous wavelet transform, the mother wavelet must satisfy an admissibility criterion in order to get a stably invertible transform. For the discrete wavelet transform, one needs at least the condition that the wavelet series is a representation of the identity in the space L2. Most constructions of discrete WT make use of the multi-resolution analysis, which defines the wavelet by a scaling function. This scaling function itself is a solution to a functional equation. In most situations it is useful to restrict psi to be a continuous function with a higher number m of vanishing moments, i.e., for all integer m less than m the mother wavelet is scaled by a factor of a and translated by a factor of b to give. For the continuous Wt, the pair varies over the full half-plane r plus times r. For the discrete Wt, this pair varies over a discrete subset of it, which is also called affine group. These functions are often incorrectly referred to as the basis functions of the transform. In fact, as in the continuous Fourier transform, there is no basis in the continuous Wavelet transform. Time-frequency interpretation uses a subtly different formulation. Restriction when A1 equals A and B1 equals B has a finite time interval comparisons with Fourier transform. The Wavelet transform is often compared with the Fourier transform, in which signals are represented as a sum of sinusoids. In fact, the Fourier transform can be viewed as a special case of the continuous Wavelet transform with the choice of the mother wavelet. The main difference in general is that wavelets are localized in both time and frequency, whereas the standard Fourier transform is only localized in frequency. The short-time Fourier transform is similar to the Wavelet transform, in that it is also time and frequency localized, but there are issues with the frequency-time resolution trade-off. In particular, assuming a rectangular window region, one may think of the STFT as a transform with a slightly different kernel where can often be written as where and u respectively denote the length and temporal offset of the windowing function. Using Parseval's theorem, one may define the wavelet's energy as equals from this. The square of the temporal support of the window offset by time u is given by and the square of the spectral support of the window acting on the frequency as stated by the Heisenberg uncertainty principle. The product of the temporal and spectral supports for any given time frequency atom, or resolution cell. The STFT windows restrict the resolution cells to spectral and temporal supports determined by multiplication with a rectangular window in the time domain corresponds to convolution with a function in the frequency domain, resulting in spurious ringing artifacts for short, localized temporal windows with the continuous time Fourier transform, and this convolution is with a delta function in Fourier space, resulting in the true Fourier transform of the signal. The window function may be some other apodizing filter, such as a Gaussian. The choice of windowing function will affect the approximation error relative to the true Fourier transform. A given resolution cell's time bandwidth product may not be exceeded with the STFT. All STFT basis elements maintain a uniform spectral and temporal support for all temporal shifts or offsets, thereby attaining an equal resolution in time for lower and higher frequencies. The resolution is purely determined by the sampling width. In contrast, the Wavelet transform's multi-resolutional properties enables large temporal supports for lower frequencies while maintaining short temporal widths for higher frequencies by the scaling properties of the Wavelet transform. This property extends conventional time-frequency analysis into time-scale analysis. The discrete Wavelet transform is less computationally complex, taking O time as compared to O for the fast Fourier transform. This computational advantage is not inherent to the transform, but reflects the choice of a logarithmic division of frequency. In contrast to the equally spaced frequency divisions of the FFT, which uses the same basis functions as DFT, it is also important to note that this complexity only applies when the filter size has no relation to the signal size. A wavelet without compact support such as the Shannon wavelet would require O complexity, but the original signal must be sampled logarithmically in time, which is only useful for certain types of signals. Definition of a wavelet. There are a number of ways of defining a wavelet. Scaling filter. An orthogonal wavelet is entirely defined by the scaling filter, a low-pass finite impulse response filter of length 2n and sum 1. In bi-orthogonal wavelets, separate decomposition and reconstruction filters are defined. For analysis with orthogonal wavelets, the high-pass filter is calculated as the quadrature mirror filter of the low-pass, and reconstruction filters are the time reverse of the decomposition filters. Doobichis and simlet wavelets can be defined by the scaling filter. Scaling function wavelets are defined by the wavelet function psi and scaling function phi in the time domain. The wavelet function is in effect a band-pass filter, and scaling it for each level halves its bandwidth. This creates the problem that in order to cover the entire spectrum, an infinite number of levels would be required. The scaling function filters the lowest level of the transform and ensures all the spectrum is covered. See for a detailed explanation. For a wavelet with compact support, phi can be considered finite in length and is equivalent to the scaling filter G. Maya wavelets can be defined by scaling functions. Wavelet function. The wavelet only has a time domain representation as the wavelet function psi. For instance, Mexican hat wavelets can be defined by a wavelet function. See a list of a few continuous wavelets. History. The development of wavelets can be linked to several separate trains of thought, starting with Haar's work in the early 20th century. Later work by Denis Gabor yielded Gabor atoms, which are constructed similarly to wavelets, and applied to similar purposes. Notable contributions to wavelet theory can be attributed to Zweig's discovery of the continuous wavelet transform in 1975, Pierre Goupilard, Grossman and Morlet's formulation of what is now known as the CWT, Jan-Noël Ov Stromberg's early work on discrete wavelets, Doobichis orthogonal wavelets with compact support, Malat multi-resolution framework, Akansu's binomial QMF, Nathalie Delprat's time-frequency interpretation of the CWT, Newland's harmonic wavelet transform and many others since. Timeline. First wavelet by Alfred Haar. Since the 1970s, George Zweig, John Morlet, Alex Grossman. Since the 1980s, Yves Meyer, Stéphane Mallet, Ingrid Doobichis, Ronald Kwarman, Ali Akansu, Victor Wickerhauser. Wavelet transforms. A wavelet is a mathematical function used to divide a given function or continuous time signal into different scale components. Usually one can assign a frequency range to each scale component. Each scale component can then be studied with a resolution that matches its scale. A wavelet transform is the representation of a function by wavelets. The wavelets are scaled and translated copies of the finite length or fast-decaying oscillating waveform. Wavelet transforms have advantages over traditional Fourier transforms for representing functions that have discontinuities and sharp peaks, and for accurately deconstructing and reconstructing finite, non-periodic or non-stationary signals. Wavelet transforms are classified into discrete wavelet transforms and continuous wavelet transforms. Note that both DWT and CWT are continuous time transforms. They can be used to represent continuous time signals. CWTs operate over every possible scale and translation, whereas DWTs use a specific subset of scale and translation values or representation grid. There are a large number of wavelet transforms, each suitable for different applications. For a full list, see list of wavelet-related transforms, but the common ones are listed below. Continuous wavelet transform, discrete wavelet transform, fast wavelet transform, lifting scheme and generalized lifting scheme, wavelet packet decomposition, stationary wavelet transform, fractional Fourier transform, fractional wavelet transform, generalized transforms. There are a number of generalized transforms, of which the wavelet transform is a special case. For example, Joseph Segman introduced scale into the Heisenberg group, giving rise to a continuous transform space that is a function of time, scale, and frequency. The CWT is a two-dimensional slice through the resulting 3D timescale frequency volume. An important application area for generalized transforms involves systems in which high-frequency resolution is crucial. For example, dark-field electron-optical transforms intermediate between direct and reciprocal space have been widely used in the harmonic analysis of atom clustering, i.e., in the study of crystals and crystal defects. Now that transmission electron microscopes are capable of providing digital images with picometer scale information on atomic periodicity in nanostructure of all sorts, the range of pattern recognition and strain metrology applications for intermediate transforms with high-frequency resolution is growing rapidly. Fractional wavelet transform is a generalization of the classical wavelet transform in the fractional Fourier transform domains. This transform is capable of providing the time and fractional domain information simultaneously and representing signals in the time fractional frequency plane.